Hello and welcome to our video on understanding quantum computing. If you've ever wondered what the buzz is all about, you are in the right place. Quantum computing is a fascinating field that holds immense potential for revolutionizing the way we process information. In this video, we will delve into the world of quantum computing, explaining its principles, challenges, and potential applications. Now, you might be thinking, but wait, is not quantum computing too complex for me to understand? Well, fear not. While quantum computing involves some mind-bending concepts, we will break it down in a way that is easy to follow and engaging. By the end of this video, you will have a solid grasp of the basics of quantum computing and be able to appreciate its incredible possibilities. So, what exactly is quantum computing? At its core, quantum computing harnesses the principles of quantum mechanics to perform calculations at speeds that are far beyond what traditional computers can achieve. Instead of relying on bits like classical computers, which are in a state of either 0 or 1, quantum computers use quantum bits, or qubits, that can exist in a state of 0, 1, or both simultaneously. One of the key principles of quantum computing is superposition, which allows qubits to be in multiple states at the same time. This means that quantum computers can process a vast amount of information in parallel, leading to exponential speedups in certain types of calculations. Another important concept is entanglement, where qubits become interdependent and can influence each other instantaneously, no matter the distance between them. Now, you may be thinking, but what are the challenges that quantum computing faces? There are indeed several obstacles to overcome before quantum computers can reach their full potential. One major challenge is decoherence, where the delicate quantum states of qubits can be disrupted by external factors, such as noise and vibrations. Researchers are actively working on developing error-correcting codes and quantum error correction techniques to mitigate this issue. Additionally, building quantum computers with enough qubits and low error rates remains a significant challenge. Quantum computers require a highly controlled environment with ultra-cold temperatures to operate, which adds to the complexity and cost of their development. Despite these hurdles, researchers are making steady progress in advancing quantum computing technologies and are optimistic about their future impact. So, how can we solve the problem of understanding quantum computing? By staying informed and curious. Learning about quantum computing can be a rewarding and eye-opening experience, and our goal in this video is to provide you with a solid foundation to build upon. Whether you are a seasoned tech enthusiast or someone new to the world of quantum computing, we hope to spark your interest and curiosity in this exciting field. In conclusion, quantum computing holds immense promise for transforming industries, solving complex problems, and pushing the boundaries of human knowledge. By embracing the principles of quantum mechanics and exploring the potential applications of quantum computing, we can pave the way for a future filled with groundbreaking discoveries and innovations. If you enjoyed this video and want to learn more about cutting-edge technologies like quantum computing, make sure to subscribe to our YouTube channel Tech Pros, like, share, and comment below. Thank you for watching, and stay tuned for more fascinating insights into the world of technology. Quantum computing, the deep dive. So, now that we have a basic understanding, let's dig deeper into the fascinating world of quantum computing. We will explore the fundamental principles that make it work, the incredible potential it holds, and the hurdles that scientists are striving to overcome. Let's turn this seemingly complex topic into something digestible and, dare we say, enjoyable. The origins of quantum computing. Quantum computing has its roots in the early 20th century with the development of quantum mechanics, a branch of physics that explains the behavior of videos on an atomic and subatomic level. The idea of quantum computing was first proposed by physicist Richard Feynman and computer scientist David Deutsch in the 1980s. They suggested that quantum computers could potentially solve problems that classical computers could not by leveraging the strange and wonderful properties of quantum mechanics. Superposition, the art of being in two places at once. Imagine being at work and on vacation at the same time. Sounds impossible, right? But that's essentially what superposition is for qubits. In classical computing, a bit can be either a 0 or a 1. However, in the quantum realm, a qubit can be both 0 and 1 simultaneously, thanks to superposition. This allows quantum computers to process an enormous amount of information all at once. Think of it this way. If you have two classical bits, they can be in one of four possible states, 0, 0, 0, 1, 10, 11. But two qubits can be in all four of these states at the same time. This exponential growth in processing power is what makes quantum computing so exciting. Entanglement, the mysterious connection. Entanglement is another mind-boggling concept in quantum mechanics that plays a crucial role in quantum computing. When qubits become entangled, the state of one qubit is directly related to the state of another, no matter how far apart they are. It is as if they have a secret handshake that instantly communicates their state to each other. Einstein famously referred to entanglement as spooky action at a distance. While it might sound like something out of a sci-fi novel, entanglement is a proven phenomenon and a fundamental resource for quantum computing. It enables qubits to work together in ways that classical bits cannot, providing immense computational power. Quantum gates, the building blocks. In classical computing, logic gates perform basic operations on bits such as and, or, and not. Quantum computing uses quantum gates to manipulate qubits. These gates are the building blocks of quantum algorithms and allow qubits to perform complex calculations. Some common quantum gates include Hadamard gate. H creates superposition by transforming a qubit from a definite state, 0 or 1, to a state where it has equal probability of being 0 or 1. Poly-X gate. X acts like a classical NOT gate, flipping the state of a qubit from 0 to 1 or from 1 to 0. CNOT gate. A two-qubit gate that flips the state of the second qubit, the target, if the first qubit, the control, is in state 1. Quantum algorithms, the recipes for success. Quantum algorithms are the sets of instructions that tell quantum computers how to solve specific problems. Some well-known quantum algorithms include Shor's algorithm, efficiently factors large numbers, which has significant implications for cryptography. Classical computers would take an impractically long time to factor large numbers, but Shor's algorithm can do it in polynomial time. Grover's algorithm provides a way to search unsorted databases faster than any classical algorithm. While classical search algorithms require O(n) time, Grover's algorithm can perform the search in O(n) time. Quantum supremacy, the ultimate achievement. Quantum supremacy is the point at which a quantum computer can perform a calculation that a classical computer practically cannot. This does not mean quantum computers will replace classical ones. Rather, it means they can handle specific tasks that are infeasible for classical machines. In 2019, Google claimed to have achieved quantum supremacy with their quantum processor, Sycamore. The processor solved a problem in 200 seconds that would take the world's fastest supercomputer, Summit, approximately 10,000 years to complete. While there is some debate about the practical significance of the problem solved, it marked a significant milestone in the field of quantum computing. The roadblocks, challenges in quantum computing. Despite its enormous potential, quantum computing faces several challenges. Decoherence and noise. Quantum states are extremely delicate and can be easily disrupted by external factors, leading to errors in calculations. Scientists are working on quantum error correction techniques to mitigate this issue. Scalability. Building quantum computers with a large number of qubits and maintaining low error rates is a significant challenge. Each additional qubit increases the complexity and potential for errors. Temperature requirements. Quantum computers need to operate at extremely low temperatures, close to absolute zero, to maintain qubit stability. This requires sophisticated and expensive cooling systems. Quantum applications. Where can we use it? Quantum computing is not just a theoretical pursuit. It has practical applications that could revolutionize various industries. Cryptography. Quantum computers could break current encryption methods, necessitating the development of quantum-resistant cryptography. At the same time, they could enable new forms of secure communication through quantum key distribution. Drug discovery. Quantum computing can simulate molecular interactions at an atomic level, accelerating the discovery of new drugs and materials. Optimization problems. Industries such as logistics, finance, and manufacturing could benefit from quantum algorithms that solve complex optimization problems more efficiently. Artificial intelligence. Quantum computing could enhance machine learning algorithms, enabling faster and more accurate data analysis and decision-making. Quantum computing in pop culture. Quantum computing has captured the imagination of many, including writers and filmmakers. It often appears in science fiction, where it is portrayed as a powerful and mysterious technology. Some notable examples include movies. Avengers Endgame features quantum computing as part of the plot to time travel and undo the chaos caused by Thanos. TV shows. Devs explores the potential and ethical implications of quantum computing in a thriller that blends science and philosophy. Books. The Quantum Thief by Hanu Rajanimi incorporates quantum computing concepts in a futuristic heist story. While these portrayals can be exaggerated, they highlight the potential and intrigue surrounding quantum computing. In conclusion, quantum computing holds immense promise for transforming industries, solving complex problems, and pushing the boundaries of human knowledge. By embracing the principles of quantum mechanics and exploring the potential applications of quantum computing, we can pave the way for a future filled with groundbreaking discoveries and innovations. If you enjoyed this video and want to learn more about cutting-edge technologies like quantum computing, make sure to subscribe to our YouTube channel Tech Pros, like, share, and comment below. Thank you for watching, and stay tuned for more fascinating insights into the world of technology.
Put it by.